a new treatment, and analysis of the effect of known phytochemicals on SARS-CoV-2 pathogenesis. In late 2019, severe acute respiratory syndrome coronavirus 2, or SARS-CoV-2, a novel zoonotic coronavirus, was discovered and detected in the Hubei province of Wuhan, China. Since then, over 109 million people have been impacted by the virus, and more than 2.4 million people have died. Because of the global state that we're currently in, we wanted to center a project on answering two dire research questions. First, can known phytochemicals therapeutically inhibit SARS-CoV-2 pathogenesis? And if so, which phytochemicals are the most effective? First, some background information. The renin-angiotensin system, or RAS, located in the body, is a hormone system that maintains blood pressure and hydroelectric homeostasis. Within the system are two polypeptide products, angiotensin 2 and angiotensin 1 through 7. The enzymes ACE and ACE2, short for angiotensin converting enzyme, are key components for maintaining this balance through protein cleavage. Unfortunately, when an imbalance occurs, several symptoms can happen, such as hypertension, cardiac dysfunction, and blood coagulation. As for the virus itself, the structure of SARS-CoV-2 is comprised of four main key proteins: the envelope, membrane, nucleic acid, and S-spike proteins, which consist of a receptor binding unit, S1, and a membrane fusion unit, which is S2. The key to binding is the receptor binding motif from the S1 subunit, where contact residues are housed. When binding, many of these contact residues engage with the ACE2 receptor via hydrogen bonds, van der Waals interactions, and hydrophobic interactions. The interactions themselves have a binding energy of negative 70.7 kcal over molecule.
Okay, so getting into the experimental design itself, our independent variables were the 9 different phytochemicals that we used, which included hydroxychloroquine, streptomycin, glycyrrhizic acid, aloe-imodin, curcumin, hesperidin, GR127935 hydrochloride, phytic acid, and RS504393. We measured all of this using Maestro's XP glide score, which was, in this case, our dependent variable. Additionally, we hypothesized that if potential competitive inhibitors of the ACE2 receptor or SARS-CoV-2 RBD are identified, then SARS-CoV-2 pathogenesis will be inhibited via the decline of available SARS-CoV-2 RBD ACE2 binding. Getting into the methodology, we would like to first preface this by saying that we used different pre-experimentation research, which helped us narrow down to 9 different phytochemicals and also understand Maestro 12. Going from there, our 9 phytochemicals were imported into Maestro, and we utilized the ligprep function to help create 3D structures and maintain different chiralities, while also shortlisting the molecules down for further docking analysis using state penalties. From there, we used Maestro's protein preparation wizard to both prepare ACE2 and SARS-CoV-2 to help remove steric clashes, fill in missing side chains, and apply the OPLS 2005 force field. As an extension, we also created the different receptor grid boxes, which we would then be able to utilize in further ligand docking analysis. From there, the 9 phytochemicals were docked to each the ACE2 receptor and SARS-CoV-2 spike molecules using Maestro's glide function, and we made additional adjustments on awarding hydrogen bonds, applying the OPLS 2005 force field, and also minimizing each of the poses to 3 poses per trial per phytochemical, which gave us a total of 9 different poses for each phytochemical when binding to either ACE2 or SARS-CoV-2. From there, we also conducted further comparative analysis and ANOVA testing analysis, which allowed us to see how the results compared amongst themselves and the statistical significance amongst each of the means of the results. Getting into the actual results, in ACE2, we can see that both streptomycin and hesperidin were front runners for binding to ACE2. Meanwhile, glycyrrhizic acid and curcumin, which from our research we thought would be front runners, actually underperformed in this sector. Additional post-hoc analysis was conducted, and we found that the true front runners here, streptomycin and hesperidin, were not statistically distinct. Additionally, hydroxychloroquine, aloe-imodin, phytic acid, streptomycin, and hesperidin were all in some form not statistically distinct in their effectiveness, though testing did show some distinction. In SARS-CoV-2 ligand docking, we could see that streptomycin once again was a frontrunner for binding. Additionally, phytic acid, which we did not expect to be a frontrunner from our research, was actually a frontrunner with a value of negative 6.885 kcals per mole. Meanwhile, we would also like to point out that glycyrrhizic acid once again underperformed in our in silico testing. Further post-hoc analysis here showed that our true frontrunners, streptomycin and phytic acid, were once again not statistically distinct. Meanwhile, glycyrrhizic acid, aloe-amodin, and phytic acid were all comparable. Putting all of these results together, we can see that streptomycin, hesperidin, phytic acid, and glycyrrhizic acid are all efficient in binding to either ACE2 or SARS-CoV-2. However, further research showed that phytic acid is not suitable as it is a D nutrient and reduces the concentration of either iron, calcium, or zinc in the body. Additionally, we would like to point out that hydroxychloroquine and curcumin underperformed in our in silico analysis, which contrasts from other ideologies out at the point. The overall interactions between the RAS system and SARS-CoV-2 spike protein have caused more than 2.2 million people to die worldwide. However, our study provides a light at the end of the tunnel, as we can see that streptomycin and hesperidin are both potential candidates for preemptive inhibition, as is glycyrrhizic acid. The phytochemicals we can see show a binding capability to provide promising results, which we hope we can capitalize on in the future.
The timeframe within the study was limited compared to most timeframes for drug discovery. The resources available were also restricted to the Maestro software, and it was only conducted in silico for health and safety reasons. Hopefully, though, in the future, the study can be used to possibly find a cure or treatment for COVID-19, as in silico methods used can help direct in vitro studies.
Thank you.